morning. Good morning and welcome to something like the 15th or 16th annual Health Econometrics workshop, returning to Ann Arbor after 15 or so years. Welcome to warm, sunny Ann Arbor. We have a great day and a half of papers and presentations. So a couple of housekeeping things. There's coffee and drinks right outside. The restrooms are directly back across the hallway. As most of you, I think, know by now that we have a slightly unusual format in that the discussant also presents the paper. So we'll take 30 minutes for the discussant presenter and then 5 or 10 minutes for the author to respond and then open it up to general questions. A few words of thanks, first of all, to Amy Taylor, my admin, who's been a huge help in setting up things locally, including the dinner last night and dinner tonight. Matt Harris and the committee did a lot of work to read through many papers that were submitted, and we chose the best few, and then also getting discussants. So again, the discussants do a phenomenal amount of work, not only to complain or provide suggestions, but also to present the papers. And that really takes, there's a very large burden on the discussants. So thanks to all of them. What I'd like to do, in case there are any stragglers coming in, is we'll do a quick round of names and affiliations in between the first two papers. So we'll get started. Marinho will start.
Should I introduce the author too, or in the audience, or should I just introduce myself?
Yeah, whatever.
All right, so hi, I'm Marinho. I'm from Notre Dame. Thanks a lot to the organizers. It's my first time in this conference. I'm happy to be here and discuss. This is a paper by Michael Keane, who's sitting over there, and co-authors Daniel Kaliski and Timothy New. So I worked with fuzzy RD. I'm an econometrician. I worked with RD before, and reading this paper, I learned a lot of interesting insights that I didn't know before. So I'm happy to be here and present, and look forward to the discussions after the presentation, but also throughout the day. All right. So as I understood reading the paper, the motivation comes from previous work that two of the authors did on instrumental variables, on the instrumental variables model. And the key sort of takeaways from that previous work, so that's actually two papers here, the Journal of Econometrics 2023 and then Annual Review of Economics 2024. I highly recommend. This is actually offers very concrete guide to practice if you're interested in this problem further than just RD. And the key takeaways is that they show that power curves for the t-test are asymmetric, even when instruments would be considered strong by practitioners, right? So just for those of you that haven't seen the power curve in a long time, so a power curve just gives you the likelihood that a test rejects when there is a true effect that's positive or negative. It's just a diagram, right? And when it says it's asymmetric, it says, well, it's easier to detect one sign versus the other. This is a problem that we may have. In particular, they have some interested insight about the direction of this asymmetry, which says the following, right? Suppose you run OLS of an effect of a program and you're suspecting that there is endogeneity, and OLS says it is positive, but it turns out the true effect is negative. That's precisely when the 2SLS t-test has difficulty in detecting. So the argument that they make is that, well, it's a pretty bad type of asymmetry because precisely when I would like this to run an IV and detect the true negative effect, that's when it has very little chances of detecting it, right? So this asymmetry power has some, a pretty strong argument against it, right? So, well, but this paper is not about 2SLS. This paper is about fuzzy RD, but the motivation comes from the fact that fuzzy RD is quite similar to 2SLS. So the question that they ask is, does the conventional fuzzy RD t-test have the same set of issues? Meaning, does it have the same sort of asymmetry problem? So what does the paper do? So first, it starts by reviewing differences and similarities between fuzzy RD and IV, okay, which I appreciate very much reading, because first of all, they're not the same thing. they are analogous, right? There's a lot of similarities, but also there's a lot of differences. Mainly, right, the fuzzy RD is a non-parametric model, and by the virtue of being a non-parametric model, when you're estimating, you have to make a lot of choice, a lot of judgment calls, and there's a lot of work in econometrics that tells you should do this, you should do that, etc. And then actually they are very clear in the paper in explaining these differences and also what makes practical sense out of it. They run a bunch of simulations and they look at this asymmetry property and see if problem and see if it's what's there or not. But in order to run the simulations, you need to first sort of pin down how am I going to estimate the fuzzy RD. There's a lot of options, right? So they pick two popular testing procedures that are out there, right? And they actually, both of them have packages available in R and Stata. And I like about the paper that they're very concrete, right? Instead of just saying, oh, this step 1, step 2, step 3. So they just take the command as it is and they apply to the simulation and see what you get, right? So the two popular testing procedures is one is based on the familiar command, older command that's been around for quite a while, and it's RD robust. And that's based on the work by Matias Cattaneo and co-authors. And that's what had the seminal paper in 2014, it's in Econometrica 2014, at the time when Matias was here in Michigan. And the second method is based on the work by Colazar, Armstrong, and others. And it's pre-packaged in the command that's called RD honest. And the key article behind that command is a quantitative economics article of 2020. So the paper here that I'm presenting, I'm discussing, actually applies these two commands and compares and see, okay, do I have the asymmetry property in both cases? What is it that I get in each case, etc. Does it matter which one I run and things like that? What is it that I recommend you guys doing? And etc. Okay, so a set of those simulations is actually grounded on a real-world example. So they took this paper by Ambers and co-authors from the AER 2020 that studies the impact of cholera deaths on rent prices in Soho, London, and they design a simulation exercise that mimics the real data example that they have in this paper, and they actually find again the same issue. And that actually lends further credibility to the empirical relevance of the problem that they're pointing at, okay? So what is it that they find? As I said, they find again the power asymmetry for the conventional t-test and fuzzy RD. It doesn't go away for moderate sizes of strength of the first stage, right? So the analogy here between an IV and a fuzzy RD is in IV, you're talking about the strength of the instrument, right? In fuzzy RD, you're talking about compliance in the first stage or strength of the first stage, okay? The simulations that they did that were based on cholera outbreak data actually shows how relevant the asymmetric problem is in real practice, right? So it turns out that, you know, there is a strong suspicion that the true effect there on rent prices is negative, right? But OLS overestimates to the point that it's saying it's 0 or maybe even positive. But that's precisely when the t-test based on fuzzy RD will have very low chances of detecting the true effect. So again, making that same point of IV that, you know, the power is small when you most need it type of thing, right? Okay, so then there's a lot more in the paper, right? I'm trying to focus on the main things here. So, but one interesting thing that I found there is they have an explanation for this asymmetry of power, and that turns out to be a general pattern. And the general pattern is a negative relationship between the estimate that you get and the standard error, right? So the negative relationships works like this. So when you have a fuzzy RD estimate that is positive, right, you get a standard error that's very small. When the fuzzy RD estimate is negative, you get a standard error that's very large. So that means that you tend to reject more spuriously positive estimates than spuriously negative estimates. And that, they showed this in simulations. They also show an expression that relates these two things And it turns out that this is related to the sign of the bias of the OLS. So again, reaffirming that same point, but studying what causes that asymmetric power. And there is this mechanics behind the scenes. And today in the presentation, I'll offer you another explanation for that same thing. Okay, so the good news of the paper is that there is an easy fix for all of this. And the easy fix is the so-called Anderson-Rubin test. You know, it's I think it's 75 years old as of now. In the weak IV literature, it's being celebrated as sort of the nicest solution for the one instrument case. And it has been demonstrated, I believe, in a paper published by Marcelo Moreira in 2009. That's the most powerful test. So it's essentially, when it comes to power, the best thing that you can do is the Anderson-Rubin test. This paper offers the further insight that it also fixes, or at least does better in terms of this asymmetry power curves. And then I'll show you a graph in a minute here that actually shows you that. How do you do the Anderson-Rubin test? That's the nice thing. It's not something super complicated that, you know, essentially it's testing, running a t-test on the intent to treat effect, right? So you run a reduced form for the outcome on your instrument, or in the case of RD, a sharp RD or the outcome on the discontinuity binary variable, and then you run a t-test, and that's the Anderson-Rubin test for the zero effect. So it's fairly easy, and that really solves the problem in a neat way of the asymmetry problem, okay? There's more stuff in the paper that I find it interesting. So the way you run the RD matters, right? So depending on how you do bias correction, or if you use higher order polynomials, which is the thing that people tend to do, right? That can aggravate even further the problem of asymmetry. So they really focus on these two main procedures, and then they have a series of recommendations at the end of which one you should go for if you're worried about this asymmetry problem. Okay, so I'm gonna take a step back, and I'm gonna show you a simple example. First of all, to sort of try to get to the mechanics behind this asymmetry problem, but also to show that this paper is actually way more general than we think, right? This is a paper about fuzzy RD, but it's a paper that largely applies to the problem of learning about ratios. So has anybody here ever estimated a parameter that's actually a ratio, right? And that turns out to appear a lot of the times, right? Even in OLS, something as simple as OLS. So if you have the OLS parameter of a simple regression or a regression with controls, that is a ratio of the covariance over variance. If you're interested, say if you regress earnings on education experience and a bunch of controls, and you're interested in the relative returns of education and experience, that's a ratio again, right? IV adds a ratio, right? So IV is the ratio of the covariance between the instrument and the outcome and the instrument and endogenous variable. And finally, fuzzy RD, thanks to its analogy to IV, also turns out to be a ratio, right? So here, just to run quickly over the notation here, X is your running variable in RD. So this is, say there is some sort of, summer school program, right? And in order to qualify for the summer school retention program, so your score has to be above or below a threshold C, right? So here, but not everybody goes to summer school. So in the numerator, you have the jump in the outcome. So that would be your intent to treat effect. And in the denominator, you have how much the probability of going to the summer school changes as you cross the cutoff. So that's the compliance of your first ERD, okay? So bottom line, ratios are everywhere. This paper is about inference on ratios being problematic. So it's an interesting paper for not just fuzzy RD, but for a lot of other problems as well. How do we learn about ratios? We typically want to do things like testing hypotheses, building confidence intervals. Most of the time, even the hypothesis test that comes out by default in your data output is testing the no effect, right? This program has zero effect, right? So this would be a no, okay, this ratio is zero versus this ratio is different than zero. Okay, great, but then once you write your hypothesis test, the next step is you need to estimate this ratio, and you need to have an approximation for the distribution of this ratio, right? So typically, right, the way that we would go about estimating the ratio is, well, if I'm interested in A over B, I find an estimator for A that is consistent, right? And I find an estimator for B that's consistent, right? And I take the ratio, and that's my beta hat, okay? then you need an approximation for that distribution. Why do you need the approximation? Because you need that distribution under the known. What if the effect is zero? Am I seeing something that's different than zero in the data? Right, so you need to approximate the distribution under the known hypothesis. Typically, how we approximate this distribution relies on the central limit theorems, Lutsky and delta method, all those good things that we learned in the first year, right? And at the bottom line, at the end of the day, right, what that amounts to is an approximation of distribution that looks like this, right? You say my denominator in the limit is going to be a constant, right? Beta hat is going to be approximated by beta, and the numerator is going to be approximated by a normal random variable that has the mean of the estimator is consistent for and some variance here. So I'm being very rough, but that's essentially what's behind to the approximation of all those examples that I showed you, those 4 examples, the OLS, the ratio, the IV, the fuzzy RD, etc. So you try to approximate the distribution of this ratio by a normal distribution. Okay? The question is this always a good approximation? Right? So in order to look at that in a, still carrying on with the simple example, let's put some more structure in the problem, and then I'll show you some very simple simulations here just to convey, right, the key of the matter here. So suppose the estimators are jointly normal with some mean and a correlation coefficient rho, okay, but otherwise a standard variance, okay? So when this is the case, right, if the means are 0 and the correlation are 0, there's a known distribution for this ratio, and that's a standard Cauchy distribution. What's special about the Cauchy distribution? It has no moment. So that's typically why, right, in the the just identified IV case, we never say that IV is unbiased, right? Because it doesn't have moments, right? So in general, this applies more generally than just the standard Cauchy case, but it's actually very hard to get a setting where ratios actually have moments in the finite sample. More importantly, in this case, the Cauchy distribution, unless it has very, very heavy tails, it doesn't have finite moments, it's still symmetric at 0, right? But that symmetry goes away as soon as you make the mean of the denominator different from 0 or that correlation different from 0. So that asymmetry comes into play. And this is what's driving this asymmetric power curve that we have that this series of papers actually allude to, okay? All right, so what I'm showing here is the actual distribution in red and the approximation that most people use in blue, right? So when red is equal to blue, we are good. When red is different from blue, we are bad, right? Okay, so here is the case where the mean of the numerator is 0, the mean of the denominator is 10, right? So you have a big denominator, a large denominator, so the true ratio is 0, right? So this is the null, right? I'm under the null, right? So the true effect is 0. So, and the correlation is a 0. So when I compare this to distributions here, and I put critical values, right? So that actually, it's the rejection rule, right? So if the test statistic is too big relative to this approximate distribution critical values, then I reject, otherwise I fail to reject. It turns out that in this case, when the denominator is large, this approximation is a pretty good one, right? Things are different when the denominator is small, right? So if I do the same exercise again for a mean of the denominator being 0.1, then you see here that I get something very close to that Cauchy distribution that has heavy tails, right? But it is still quite symmetric here. When you look at the rejection rate, this is 4 times more than what you had intended to, right? So this is there's a problem with the rejection rate, right, of not controlling size here in this case. So the approximation is pretty bad. Once you change the correlation coefficient from 0 to something that's very large on the positive side, you start to get the asymmetry. So here you tend to reject more on the positive side, and if the correlation coefficient is negative, then you tend to reject more on the negative side. So what's the takeaway of this? So there's a problem with the size of the t-test for ratios when the denominator is small, which makes sense, right? Denominators, when they're small, right, you have this noise around 0, so this ratio explodes, right? And you're trying to approximate that by something that assumes a denominator that's constant and different from 0. So it makes sense that this approximation is bad. So that turns out into a problem with size, right? And the asymmetry that we saw, right? You tend to reject more in one of the two sides, depending on the correlation between these two coefficients. Do our four examples suffer from this problem? So if you go back to OLS, usually, or most of the time, you don't have this problem because that denominator of OLS is a variance that's positive and typically large. So unless you're very, very special situations, you don't typically have this problem in OLS. So that's why nobody talks about, you know, the weak IV equivalent of OLS unless you are in some specific settings where you have a lot of variables, etc. What about the ratio of coefficients of education experience? Yes, when the returns of experience is small relative to how precisely you can estimate. Definitely IV, you have that issue when the instrument is weak. There's a whole literature about that of decades now. And then definitely in the fuzzy RD, when the compliance on the first stage is small relative to how well you can estimate that first stage. Okay, so bottom line, you have the size problems in potentially three of those examples that we saw in the beginning. Now, the paper is not so much about the size, the paper is about power. So how can we see power that are similar in power in this simple example? So let's go back and now let's simulate the two distributions, assuming the true ratio is not zero, and see how often we reject the false no, right? If we design a test for zero, but if the true effect is not zero, how often do you reject, okay? So first we start here again with the small denominator, okay? And I assume that the true ratio is 10, right? So it's a positive true ratio, so that's different from zero, it's bigger than zero, right? And it turns out that I reject approximately 10% of the time. Well, I rejected the no 20% of the time. So I'm rejecting more the no effect than the effect that's positive, right? I would like to detect the positive effect, but I actually detected less, so there's a problem there, right? When I flip the sign of the effect, right? So suppose now I'm looking at the ratio that is on the negative sign, right? So things flip around, and it turns out that the rejection rate is almost twice as the rejection of the no effect, right? So what's the takeaway of this exercise? The conventional t-test reject no effects approximately 2 times more often when the true effect is small and positive. So this is something that we don't want, right? But on the other hand, negative effects, right, for this example, right, I reject that 2 times more often than no effects, right? So this is something that's good if we had controlled the size in the first place. What's the solution of the problem? And this is the solution that in the paper they have, right? Well, is to rewrite the no, right? So if the denominator is different from zero, right? If it's zero, you'll never learn anything about the ratio. If it's different from zero, testing this no hypothesis turns out to be the same as testing that the numerator is zero, right? The Anderson-Rubin test is just a t-test for that numerator. So it's simple as that, right? And it's much easier to approximate the distribution of the numerator, okay? So this is a couple of power curves that came from earlier work by Michael Keane and Timothy Neal, right? So here you have the power curve for detecting true beta effects that are different from zero. So the black line is the power curve of the conventional t-test, and the blue line is the power curve of the Anderson-Rubin test. That is the one about the reduced form. That's the one just about the numerator, right? So you can see exactly the behavior that I showed you in that simple example, right? Except that the signs here are flipped, right? For small negative effects, you actually reject less than you reject no effects. But for positive effects, you reject way more, right? The Anderson-Rubin test is the so-called unbiased test, which means that regardless if it's positive or negative, you're going to reject more than the no effect. So this is the desirable property of Anderson-Rubin, and it turns out that Moreira has demonstrated that this is the most powerful unbiased test that you can run. So this is the power envelope that we're seeing here, okay? All right, so let's go back to the fuzzy RD specifics. So how do we estimate this ratio in fuzzy RD? So typically, you use a local linear regression with a triangular kernel to estimate the objects of this ratio. So you're estimating essentially it's the average of an outcome close to the cutoff if you're above or below, and the average treatment rate close to the cutoff if you're above or below, and then you construct your beta head in this way, okay? You have to choose what local means, right? So that amounts to choosing the bandwidth, right, in technical terms. And you have to do some bias corrections. So this is a no parametric problem. You don't know the shape of this conditional mean function in general, right? So that amounts, if you approximate that with a linear regression, even if it's local, there's going to be some bias involved. So you have to take that into account. And it turns out that it matters for inference, right? The literature has, at least the theoretical literature, has agreement on doing 0.1, and there has some disagreement on doing 0.2. When you go to practice, there's even more variance on how people do these two things. The paper looks at two main branches of the literature, two main methods. One is, as I mentioned earlier, methods by Matthias Cattaneo and co-authors, and other one is a method by Michael Colazar and co-authors. So the first method they are calling here RBC, so that's called robust bias correction. Essentially, in a very quickly here, a review of what that method does, right? It essentially estimates each one of these quantities here and estimates the bias, and it subtracts the bias. So it estimates, it tries to correct for the bias right at the estimation stage. And it chooses the bandwidth in a way that is mean squared error optimal for each one of these estimates, right? And that's it, and then you do the t-test as you would normally, right? It also inflates the variance of the estimates by this, because of this bias correction. Okay, so this is method 1, RBC. Okay, what does method 2 does? Well, we estimate all of these 4 quantities, but it doesn't correct for the bias at the estimation stage. He estimates the bandwidth also in a mean squared error optimal way, but for that, it considers the worst case bias. So it assumes that you, researcher, believe that these conditional mean functions live in a family of models, and it takes the worst case and it says the bias can be as bad as this. And then it takes that as the worst case, and when it constructs tests or confidence intervals, it takes the critical value of that worst case distribution. Okay, so the paper by Mike and co-authors looks at the two main procedures. It looks at other things too, but it focuses on this too. And this is a very nice scatter plot for one of the various simulations they run. And it shows you that negative relationship that I described in the beginning, right? So here you have the standard error of an estimate, and here you have an estimate for the fuzzy RD. Left is RBC, and right is BST, so method 1 and method 2. Right? So what is shaded in red here are the points, the estimate standard errors that lead to rejection. So the first thing to see here is that there's a negative relationship. Even if the true effect is 0, you actually get that when you estimate the effect to be positive, the standard errors are tiny, so you tend to reject more on the right than on the left. When you look at BST, right, they have the same problem essentially, except that it's a little bit worse here. So if you look at the table where it shows you the results, the size, the rejection rate are pretty much correct for both methods, except that BST is a little bit more conservative. But the percentage of rejections on the positive side is definitely higher for BST and RBC, and that essentially comes from this lack of bias correction on the estimation stage. Okay. What happens if you do the Anderson-Rubin for the reduced form coefficient? That relationship disappears, right? So now we are in we have a flat relationship between standard errors and estimates, and most importantly, you have the rejection rates being approximately the same on both sides, and again, being a little worse for the bounded second derivative, the BST method number 2, okay? All right, so I'm out of time, so let me just close the presentation with a slide here and some points for discussion and further conversation. I think, you know, that there's a very nice, sort of an easy connection that this paper could make with the literature on impossible inference in econometrics, which I have done some work, but a lot of people have done some work on this, especially in the context of RD. And what the literature on impossible inference says is, it says that in some context, in some classes of models, it is impossible to find a hypothesis test that has this or that feature, right? Now, I need to tell you more, right? So in this paper that I wrote with Marcelo Moreira, we categorize the literature into 2 types of impossibilities. There's type A and type B. Type A is a little stronger than type B. So what does type A says? So type A says that if your model satisfies a set of conditions that we write down in the paper, every test that you can ever come up with, and this is a finite sample result, it relies on no asymptotic approximation. Every test that you can ever come up with has trivial power, which means that if your test control size, the power is going to be no bigger than size. So this is what we call type A. Which examples suffer from that? Well, there's a paper 100 years old that shows that even something simple as testing means suffers from that, and the sharp RD case suffers from that problem A, right? How is the solution of that? You have to restrict the class of models, and that's what Armstrong and Colozar do, right? By bounding the second derivative of the conditional mean function. Okay, what's the impossibility type B? So the impossibility type B says the following: in some settings, right, if some assumptions are satisfied, it's impossible to find a confidence set that is bounded all the time. Well, why do I say this here? Well, a t-test inverts into a confidence set that is bounded all the time, right? Because it's estimate plus or minus standard error times 2. So that's a bounded confidence set. Which models are known to suffer from that? Well, ratios and IV. Now, one thing that's nice about fuzzy RD, and that's the connection that I was alluding to that would be nice to be made here, is that fuzzy RD has both problems. The paper that's cited there by Nowak and Roth, a recent Econometrica paper, proposes doing the Anderson-Rubin test plus the bounded second derivative, the method 2 that we said earlier. And the reason why they do that, although they don't say it in these terms, is because it tries to solve both problems. But it's interesting to see in this paper that when you look at the simulations, the AR test plus method 1 does a little better. So it's interesting to ask the question, why is that, right? And I think we can talk about this further, but I suspect that it has to do with the BSD method always ensuring against the worst case model. So I think for that, I think it would be helpful to look at simulated power curves for the fuzzy RD. I think it would be nice to have those in this paper and try to relate that to the optimality properties of the BSD method. So it does have something to say about optimal power curves, and definitely to run simulations under the worst case DGP, which this method insures you against. So we're not always in the worst case DGP. So there's a very nice point to be made in this paper, which is, well, if I'm not always at the worst case DGP, is it worth taking the worst case correction approach? And I think that would be wonderful to have that discussion in the paper. And so far, I think the simulations pointed that it's not always worth insuring against the worst case. But this is all I have, and I'm happy to talk further to anybody. Thank you.
Thank you. Michael Keane will respond.
Okay, thanks a lot, Marino. Actually, that was great. There's nothing really to respond to. I would just let me emphasize a couple points. I'm trying to get a message across for applied people to hear, which is that regardless of whether you're doing instrumental variables or fuzzy RD, you're going to have this issue that, just to keep it simple, if the OLS bias is positive, then if you run your IV or your fuzzy RD and you end up getting a positive estimate, you can assume your standard error is too small, right? And if, on the other hand, if you get a negative estimate, you can assume your standard error is too big, right? What I would strongly urge applied people to do is to always report OLS, right? Because in many papers this is not done. Right? It's obvious what OLS means when I'm talking about IV. When I say quote OLS in the fuzzy RD context, that would be what you get if instead of doing fuzzy RD, you simply run a sharp ID ignoring the endogeneity of the treatment. And that would be analogous to OLS, right? And by showing that estimate and comparing it to the either IV or fuzzy RD estimate that you actually get, that comparison sort of tells you what regime you're in, right? Are you in the regime where you would be worried about the standard error being too large or too small? And that's very informative in terms of interpreting the results. So basically, if your OLS versus endogeneity adjusted estimates are far apart, you're going to be in this regime where your standard error is probably too big, right? And in many cases, that might be good news. You might you might then be able to run the AR test and get a stronger result, right? On the other hand, when you're in the context where your endogeneity adjusted and OLS estimates are close, that's the case where people typically say, oh, I'm happy. OLS and IV are similar, so everything looks good. That's when you need to worry. That case where everyone thinks they should be happy is when you need to worry. That's when your standard error is almost surely too small, right? And that's when you're likely to find, if you run the AR test, that your result that you thought was significant really isn't. Right? So, but for someone trying to interpret your results, it's very important to be able to see both the OLS and the endogeneity adjusted result in order to tell what regime you're in. Other than that, I'm on the in the Journal of Econometrics paper and in the annual reviews papers, we show what the analytical power curves look like for IV. Currently, the fuzzy RD paper only has simulations. We're working on the analytical power curves, but it's quite a bit harder because you have to account for the fact that the bandwidth is estimated. So we've got simulated power curves, but I think we're pretty close at getting the analytical power curves accounting for the bandwidth. Anyway.
We can open it up for questions about something new to worry about.
Yeah.
I have a little comment about what you say, bias relative to OLS. When you're presenting it, there's obviously a precedent for that, but Stock and Joe will do is that when you report like first stage statistics, they like to think about it bias relative to OLS. So there's really already a precedent and some discussion. Like maybe you want to look at that when you're discussing it, because that's how they frame it. They frame it to read
But
Go ahead.
the point they're making is very different.
Of course,
Yeah,
of
yeah,
course,
okay.
it's much different, but
Yeah.
that's how they turn
Yeah.
their head and say, you report both of them. So there's some precedent and some discussion about that, which I think it's important to discuss. Yeah, flips it, it's different.
Okay.
I have a question for Marino. I just know, maybe I understand, so you were discussing about a ratio at some point, and it seems to be that the mean was really small, right? When you were dividing by a really small mean, is there something there to the signal to noise ratio where it's so small that the noise is bigger and so sometimes you reject or under reject? It's more like maybe that's what might be driving some of these results, that you cannot detect the difference between the very small number and the noise.
Yeah, so what causes the problem is the signal to noise ratio. So in the simple simulation, I fix the sigma at 1, and I vary the mean, but you're correct, is how big the mean is relative to the standard deviation that caused the problem. So the mean could be very small, but if the standard deviation is tiny, then you're fine.
Yeah,
It's the signal to noise ratio, and that's what the F-test in the first stage does.
And you cannot detect between like the true value because it's just too noisy and sometimes it rejects, sometimes it doesn't, and then you get.
If I can just follow up on that, so I was, as you were presenting, I was thinking, as an applied person, can I look at the denominator distribution first? So without looking at the numerator distribution, right? Look at the denominator distribution and ask that question. If my inference on the denominator statistic suggests that I'm really far away from zero,
So I'll give you some
is that okay or not?
So just some practical advice, okay? If what we show in the Journal of Econometrics paper and in the annual reviews paper is if your first stage F is up around 50, 50 or a bit higher, then this power asymmetry problem is not too bad. Okay, so this is practical advice. So there's this common rule of thumb of the stock yoga sort of rule that if your first stage F is at least 10, you're okay. But the point is, if your first stage F is 10, then it's true that size distortions are going to be trivial. So we show that, right? However, the power asymmetry problem we're talking about here will be extremely severe, right? So if your first stage F is about 10, your test might have a size pretty close to 5%. Your 5% test may really be about 5%, but essentially all the rejections are going to be on one side. So you've got correct size, but all the power will be on one side, right? You have to crank the first stage F up quite a bit more for the power to be decently symmetric. This is a rough guide. All right. So that's another message of these papers, that the people should be wanting to see significantly higher first stage Fs than we're used to demanding.
Yeah, also from an applied perspective, I'm just trying to wrap my head around whether I'm taking away the correct thing. The discussion kind of emphasized that these issues with asymmetric power kind of tend to show up more when the denominator of your estimate is small. But in the context of RD, I guess that denominator is the effect of the running variable on whether or not you're treated. And if that's really small, then I would have thought like maybe it's not a very good running variable, or it's not a very good RD. Like if I'm saying, oh, you need an SAT of 720 to get financial aid, but then when I look at it, it hardly bumps you at all to get financial aid, then maybe like the thing to say is like, oh, this wasn't a really good RD to begin with, because crossing the threshold of a running variable really didn't bump your treatment status very much. And so I guess I was just wondering, like, how critical is it that this idea that the denominator is small, is that really important for this power asymmetry problem? And if it is, then like what do we make of the RD?
This just goes back to what he was saying back there, is the signal to noise ratio. So it's how small it is to how precisely you can estimate it. It's fine to have a very small first stage, as long as you can estimate it very precisely. So it's the signal, so that's why we look at t-test for the first stage and f-test, because that's like, it summarizes that ratio in one number.
And something I like to play with is sometimes you do simulations where you put the coefficient, whatever it is, very close to 2 times that of the coefficient. So it might be big if you wish, but if it's not 2 times the standard error, you just kind of put it there. Sometimes it flips and rejects and doesn't reject. So you really need to look at both things. It might be big, but you need to look at relative to your standard error and the precision there.
Yeah, so remember that, yeah.
What Michael the point that Michael makes is that in very realistic settings, even if you may get a number that's large in the first stage, you still have the problem.
Correct.
Real world examples.
I may be missing some of the details in the econometrics, but what if you have a situation where you have multiple IVs? So theory suggests that you want to do a joint test on a set of data. Does this apply in that case? Or
So
is this
you have
only
multiple
single?
IVs. Okay, so one thing that's nice about the fuzzy RD setting is it's like you've only ever got one, right?
Yeah.
Now, but when you go back to instrumental variables, of course, then sometimes we have over-identified models with multiple instruments, and then things get a bit trickier, right? Because the AR, the Anderson-Rubin test, it's still really simple. In that case, the Anderson-Rubin test is still just the F-test from regressing the outcome Y on the full set of instruments, okay? But the problem is it's no longer the most powerful test. right? And in fact, there is no, there is no most powerful test in that context. And but I think the consensus in the literature, I think, is that the best you can do is this Kleibergen test, which we talk about in the Journal of Econometrics and the AR paper. So you could look that up. Another really important, these AR tests are just trivial to do. So it's puzzling, you know, it's frustrating. People just don't do it all the time.
All right, thank you very much. We'll move on.